All right, welcome everybody in the lecture hall, welcome everybody on Zoom. So today we are going to continue what we started last time with the white column stores, namely HBase, the open source version of Bigtable. So this is where we left. As a reminder, we have, well, a Bigtable with a lot of rows, can be billions of rows, a lot of columns, it can be millions of columns, but it's sparse. There's a lot of cells that are actually empty, and the columns are grouped in column families, and the column families are stored together. So as I said last time, it's like a wedding cake. So we cut in partitions horizontally and vertically. Horizontally, it's the intervals of rows that are called regions, right? These are contiguous sets of rows with a min inclusive and a max inclusive. And then that together with a column family gives us what we call a store for the purpose of the physical layer, right? So we have plenty of these stores. It's really like a two-dimensional grid, as many stores as the combinations of regions and column families. Then we saw that physically, the way that the stores are stored on HDFS is that we list the cells. It's like the battleship game. So A1, A2, B1, B2, and so on. And every time we have on every row, well, technically on the physical layer, the way I put it on the slide, these are rows. So every row has one cell, A1, A2, B1, B2, C1, C2, and so on, right? So left to right, and then top to bottom. Moreover, we can have several versions of the same cell. So here there's only one version, right? But in general, we might have several versions of the same cell. So basically, it means you have all the versions of cell A1 in descending order, the latest version first, then all the versions of cell A2, then all the versions of cell B1, then all the versions of cell B2, and so on, right? So it means we first sort by row ID, then we sort by column name, the column family is the same within the store, and then we sort in decreasing order of the versions, right? And then we just get a list of these values. Something else that there's only one slide to quickly talk about that. Whenever you access the database system, there is the concept of atomicity. It means when multiple people are accessing the server, the database server, what happens? Can they do things at the same time? Well, in classical databases, like in the 1970s, we could make sure that two users do not access the database at the same time, right? It's one after the other. More exactly, we can make it look like they are not accessing the database at the same time. There's ways to cheat about that. But basically, it means that if Alice connects to the database system and wants to modify something, then whoever else, like Bob, needs to wait until she's done, until she can make her changes. That's called a lock. In big data systems, we are a bit more flexible than that, meaning that if a user tries to modify some data, this is not going to block the whole database. It's only going to block the row in which you are doing something. So if Alice is making an update to a specific row of the Bigtable, then Bob would be able to make updates to another row of the same table, but just not two at the same time, the same row, right? So we say that there is a lock, and we say ACID, remember, right? The paradigm of relational database systems, atomicity, consistency, isolation, durability. We do that at the level of a row and not at the level of the whole table. It makes sense, right? Because there are billions of rows, millions of columns that would be just impractical to block the entire table. Okay. And this is where the versions come from, by the way. The fact that we have a linear list of versions, version 1, version 2, version 3, is before we make the users queue in this way, that they wait for each other. It's like at the post office when there's only one shelter that is open, so there is a specific sequence. That wouldn't be true in general if we didn't have the lock. All right, parenthesis closed. This is just to say that they cannot update the same row at the same time. So now, one more step. When I listed these cells and all the versions of every cell, in fact, what I have listed on the physical level are called key values. Yes, again, key values, just like the key value model. So it's just in the end, when you store a store physically, it's a list of key values. What are the keys? Well, the keys are basically the row ID and the column family and the column name and the version. That together identifies the value. And then the value is whatever you have in the cell, right? So in the end, when you store the table, then you just list all of the values associated with the key that tells you where in the big table it's located. For whom is that clear? For whom is that clear? Okay, awesome. So now I'm zooming in, and don't be scared, these are more physical details. If you actually look at the details of that key values, remember that on disk, it will have to be zeros and ones. It always has to be zeros and ones in the end when you store on the disk. I told you everything is binary in this system. So even the row IDs and the column names, this is all sequences of bits. And the same goes for the value. So now, when we zoom in, we notice, oh, that's interesting. So we don't store just the key and the value. We also store the key length and the value length. What's that? Well, the key length is just the number of bits that the key is made of. And the value length is the number of bits that the value is made of, right? Because that's variable, right? It could be any size, the column name or the row ID. The value could be maybe just a number, or it could be a huge XML document, right? So the length here can vary. Just imagine that this is elastic, right? This can be larger or smaller here. So the length of the key and the length of the value give us information so that we know exactly how many bits we are supposed to read to get the key and how many bits we are supposed to read to get the value, right? In practice, the key length and value length are given even in number of bytes, not on bits. So the bits are the zeros and ones, and the bytes are groups of 8 bits, right? So typically, if you have an integer between 0 and 4 billion, then that takes 32 bits to store. 2 to the power of 32 is 4 billion, roughly. And the number of bytes would be 32 divided by 8, so 4 bytes. 4 bytes is 32 bits, okay? So we store the length. Now, here's a bit of why we need the length. Because if I just give you the key with the value, you already know how many bits, right? But in practice, we need to understand what a prefix code is. Now, I will have to do a bit of history, because now we have mobile phones, so the look and feel of making phone calls is different. Who has ever made a phone call with a fixed landline phone? Who never did a call with landline phones? Some of you, okay. Well, if you try to call somebody with a landline phone, you will notice something. So first you pick up, then there is this tone that it wasn't there at first in the history of phones, but then they added it to make clear that the line is working. It's an A, and then you start pressing the keys. And this is actually sending a mix of 2 frequencies in this phone. So it's a mix, 1 frequency for the row and 1 frequency for the column of your keypad. But then as soon as you press a key, the tone stops because it knows you're starting to dial like 0 and then 44, 6, 3, 2, 1, 1, 1, 1 if you're calling ETH. And then as long as you press the first 9 keys, nothing happens, right? And when you press the 10th one, the 1, then suddenly it's dialing. How does it know? Because phone numbers often have 10 digits, right? But there are also the emergency numbers that have only 3 and so on and so on. So how can the phone know that this is where it stops the dialing and that it can now dial the number? This is because of a prefix code. And this is the magic. So here it's an example. I'm not getting into the detail, but this is an example of prefix code that allows you to encode a sequence of integers. It's called the gamma code. And it's done in such a way that if I just give you the sequence of zeros and ones, right now I have no idea where it starts and where it stops, right? But somehow I have this magic code that you don't need to know the details of that. It's just to show you that just looking at that, I know that I need to read 1 more bit because there's 1 before the 0. Then here, looking at the number of ones, I have 8 ones, so I need to read 8 more bits. That gives me again 2 ones, so I need to read 2 more bits. 3 ones, so I need to read 3 more bits. So you see, there are magical ways of cheating and telling you how many bits you will have to read. In that case, the cheating is by putting plenty of ones followed by a 0, and the number of ones tells you how many more bits you need to read. So this is a trick, right? And in fact, this is called the prefix code when you can do that. And then it means that you can put these numbers one after the other without any separation, and you are able to separate them back. And in fact, you can do it as an exercise. Take a list of phone numbers, random phone numbers, concatenate them without any spaces, just a concatenation of phone numbers. Even if you forget where the boundaries were, you can actually reconstruct the boundaries because the phone numbers are structured in such a way that you are able to know where it stops, right? Because, for example, emergency number starts with a 1. When it starts with 0 and then another 0, you know it's international. If it's 044, you know it's Zurich, and there's a few more and so on. So this is the idea. Now, if I come back here of this key length, value length, it's a cheat sheet that tells me, okay, that's how many bytes I need to read for the key, and that's how many bytes I need to read for the value, okay? And again, that's because the key values are concatenated with each other, just like the example I gave with phone numbers. And so that way you can read and parse back the key values to keys and to values. Okay, so that's the trick, okay? That's the idea. And then if you zoom in, so this is now inside the key. I zoomed inside the key, and what do I see? Well, I see, not surprisingly, I told you what the key is made of, right? There is the row ID, there is the column family, there is the column name, and there is the version, right? So it's not surprising that you see them here, right? There is the row ID right here, the column family right here. It would be the same for the whole store. The column name or qualifier right here, and here that's the version with the timestamp. It's all here, right? This here is an extra bit. This is for marking deletions. If you delete a value in a versioning system, you don't actually delete it. You just mark it as deleted, right? It's like the dustbin of an operating system, right? You just mark it as deleted. So row ID, column family, column name, version. The 4 together give you the key. And now we need, again, because the size can vary, it's elastic. So we need the length of the row ID that tells you how long this is. So now we know where to stop reading. Then we have the length of the column family. Then we know how many bytes to read here, and we know where we stop. And then the timestamp, it's always 32 bits. That we know, it's a fixed number of bits. This is exactly 1 bit or a fixed number of bits, so we know as well. That is variable. How do I know how many bytes there are in there? How do I know where to stop here? Because I don't have the column name length, right? I only have the row ID length, the column family length, but I don't have the column name length. How can it be? How do we still know it? Can we compute it in some way, or can we infer it in some way? How do I know how many bytes there are in the purple zone here, the column qualifier? So the row length is always an integer on 32 bits. So I read 32 bits, I have the row length. Yes, yes, a correct answer on the Zoom chat.
Yeah, so I one answer, so the length and column
yeah. Go ahead.
And the key tab length.
Yes, so basically this is the idea. Here, remember that we also know, I just need to rewind a bit, we also know the key length from outside, right? What you saw on the other side is just a zoom in into the red zone, the key zone, right? But we know the key length. So what is the key length? That's the total size of all of that. This is the key length. So because I read the key length before, I know how long this is in total. So I know how long this is. This is fixed. This I know from here. This is fixed. This I know from here. This is fixed. This is fixed. So it's just a subtraction. The key length minus this, minus this, minus this, minus this, minus this, minus this length gives you what's what remains. So you can save the column qualifier length. You don't need to store it because of that. For whom is that clear? Right? It's just a subtraction. Okay. So it's low level. We are really talking about bits here, but this is kind of how it works, right? And in the end, we just store the key values one after the other like this. And thanks to the magic of storing the length in there, we know exactly when they start. We know exactly when they stop. We know exactly when the row ID starts and stop. We know exactly when the column families start and stop. We know exactly when the column qualifiers start and stop, thanks to the subtractions. Okay. Now, so physically, in a file, we will call them H files, right? So all of these key values will go into the file on HDFS, an H file. It's just a huge list of key values, really. Maybe, I don't know, 1,000, 100,000, 1,000,000 key values, like just a lot of key values concatenated one after each other, and they are in an H file. Now, if this is all you do, and you store an H file as a sequence of key values and that's it, imagine that there's a lot of them, 100,000, and you need to locate one in the middle. That's not going to be very convenient, right? Because you have to go through them. Maybe you can save yourself some efforts with binary search, just like looking up in a dictionary if the keys are ordered. But it still takes a while. Plus, it's on HDFS. So HDFS is even slow. So we need to optimize a little bit and accelerate things. And we are going to cheat again. We are going to use an index. So what we do is that these key values that are in the H file, we are going to group them into blocks. However, I'm not going to say block, I'm going to say H block. The reason is I don't want you to confuse them with HDFS blocks. When I say block, it's really an HDFS block, 128 megabytes. But here we are talking about a different kind of blocks. This is blocks that are specific to H files and to HBase, right? And these blocks have a size of 64 kilobytes. This is the size of my blocks, right? So again, it's not the same size because for HDFS, it was 128 megabytes. Here it's 64 kilobytes. Now there is a bit of a difference. In HDFS, the 128 megabytes is exact. You cut it exactly at 128 megabytes, bam, this is how you separate in HDFS, right? Only the last block might be a bit shorter, but otherwise it's absolutely exact. In an H file, you don't cut exactly at 64 kilobytes. If the 64 kilobyte would cut a key value in two, then you don't let that happen. You let the key value finish, and then you finish the H block, right? So in practice, the H blocks are going to be larger than 64 kilobytes just because you wait for the last key value to stop, right? In fact, if one of the key values, the value contains an XML document of 10 megabytes, then your H block will be 10 megabytes, right? If that actually happens. Okay, so this is just in order to organize things. And what happens is that we have this cheat sheet on the left. It's an index that accelerates the lookup. So if I did not have anything, the file would just be a list of key values, and that's it. And then you would have to search like in a dictionary, right? Because the key values are sorted by key. So you would just go in the middle. Is it larger or smaller? And then you go here, just like in a dictionary, right? But this takes time. Now, what I'm doing is that I add some structure on the side that tells me this here is the first key of this H block. This here is the first key of that H block. This is the first key of that H block. This is the first key of that H block. Now you understand that this accelerates things because now if I'm looking for a specific key, I can load that into memory. This is still on disk, right? But that I can load into memory. And now if I'm looking, for example, for key 14, I don't need to look at that just yet. Let me just look at this index here. Where is 14? Well, that's a much smaller list. It's between 11 and 17, right? So now I know that key 14 is going to be in that zone right here, right? So that accelerates the lookup because now I can directly jump to that H block right there. So this allows me to specifically read what I'm interested in. Okay. So in summary, just to make sure that you don't lose the big picture, a big table is made of billions of rows and millions of columns. The rows are partitioned horizontally in regions with a min inclusive and max exclusive value. And the columns are partitioned vertically into column families, and the intersection of one region of rows and one column family gives you what we call a store. And a store will be persisted to HDFS as one or more H files. An H file is a sequence of key values, an ordered sequence of key values. So it's ordered by key, where the key is made of the row ID, the colon qualifier, the colon name, and the version, and that uniquely identifies the value. And we saw that we smartly store the length just to know where the key values start and stop in order to read them back. Furthermore, to accelerate the lookup of a specific key value in that sorted list of key values, we cheat and add an extra structure on the left that accelerates the lookup by directly telling you where you need to look. Okay, so this is in essence what happened. Who is with me? Okay. Now, let's look at the levels of physical storage. Again, now this is a wrap-up of all the levels that we have to consolidate that knowledge. So the highest possible level, apart from the entire database, of course, is that of a table, this enormous table. Then the table is partitioned horizontally in regions. Then the regions are partitioned vertically again in stores, right? So a table can have several regions. A region can have several stores. The stores are persisted to 1, 2, or more H files on HDFS. The H files consist of 1 or more H blocks, right? 64 kilobytes or more, because the H blocks elastically adapt to the last key value. They don't stop abruptly. And an H block is made of 1 or more. Yes, I hear it louder. 1 or more key values, exactly. Thank you. Yeah, exactly. So these are all the levels. You see, table, region, store, H file, H block, key value. These are the physical level. Of course, the user doesn't see that. From outside, you don't know. This is really the internals, the tricks, physically how we store all of that. Okay? So now, let me bring you to the next engineering trick, because these are really smart people, the team who designed all of that. I'm going to give you a problem to think about, because this here, this H file, is a sorted list of key values. Sorted. So key 1, key 2, it's all sorted alphabetically or lexicographically. First sorted by row ID, then sorted by colon family, then sorted by colon qualifier, then sorted decreasingly by version. Now, this can be a problem, because when we have a file like that, where the key values are sorted, remember that it's persisted on HDFS, right? So on HDFS, the only thing I can do is write a new file or append at the end of a file. What I cannot do is randomly modify the file. I cannot just in the middle of the file add a key value. Imagine that I have to add, well, okay, these are integers. So let me say we have to add key 7.5, right? Of course, that's later, but key 7.5, you would have to insert it between 7 and 8. But that you cannot do in HDFS, right? This is impossible. So what do we do? Because Bigtable or HBase, they allow you to insert values. You can insert, I showed you, right? Get, put, delete, scan. So in HBase, you can absolutely add new key values. But does it mean that whenever you add a key value, you need to wait forever until the entire H file gets rewritten to HDFS? That would be super slow, right? So this is kind of a mystery. So how do we solve that? How can we insert new values into our table in a way that we don't need to rewrite the entire H file every single time we have to insert a key value? That would be highly inefficient. Who understands the problem? Right? Okay. So it looks like complicated, but in fact, you will see it's beautiful. There is a trick that the engineering team thought of. So this is what I've just shown you physically. Now just another view. So on disk, what do we have on HDFS? Now you connect to HDFS and you look, you will see that there are folders, of course, but inside there are these H files. And inside the H files, you have the H blocks and the file. But there are several H files for the same store, right? Now, the trick is this. That's the first part of the trick. The trick is the key values are not all on the disk. More exactly, the fresh key value that I've just created very recently, let's say in the past hour, in fact, they are not just yet on the disk, they are in the memory. We call that the mem store. So these are all the fresh ones on the top, and what you see at the bottom is the older ones. the ones that are old enough that we actually persisted them to disk. So in other words, when somebody modifies a key value, I don't actually write anything to disk. I just accumulate the key values in the memory of my machine. So the memory that's efficient, right? That I can put very quickly and access very quickly the key values, right? So now, if I have a small animation for what's happening, I have my mem store. So let's say now the mem store is empty and I only have 4 key values that are persisted on HDFS. A user issues a put query and adds key values into the system or updates a key value. What we do is we put it in memory, in the mem store. So that's a new key value that was just freshly created. Here's another one. Here's another one. Oh, but now the memory is full. So many people have been adding key values that now we cannot add anything more in memory. What do we do? Well, this is called flushing. We flush all of the key values to disk. What does it mean? I need to sort them because here they are just in memory. So let's sort them. And once we sorted them, we write them in the order, in increasing order of keys. So increasing row ID, increasing column, family, increasing column name, and decreasing version. And that's it, nicely organized in H blocks, right? But you see that from the point of view of HDFS, I just wrote one file in a single write. And that I can do with HDFS, right? I didn't try to modify with random access. Okay, so the trick is really that you sort and directly flush an entire H file in one single write on HDFS. Now, to be even more exact about the sorting, we could, of course, randomly accumulate the key values in memory without any specific order and then sort at the end. But in fact, what the system does is that it keeps them ordered in memory. So we know in computer science, we have data structures, typically trees, that can be used in order to preserve the order in real time in the mem store. So technically, we keep them ordered in the mem store. And when we flush them, it takes a linear time. We go through them in the order in which they are and flush them to HDFS. Who is with me? Okay. It's very complex. I wonder it's probably the most complex lecture of the entire semester. So I really want to make sure that I drive you through this without losing you. Now here's another problem. The other problem is, since we do not store all of the key values on disk, but only the older ones and the fresh ones, we have them in the memory, what happens if the computer crashes? Because if your computer crashes, the memory goes away. This is wiped out, so you lose everything. So it means that if the computer crashes, we come to the question on the Zoom chat, if the computer crashes, we would lose everything, right? There is a question on the Zoom chat. So let me answer this question here. So what happens if a key value, well, the key already exists. There was already a value in a specific cell of the table, and I want to update that value. I want to change it. It was 1, and now I want it to be 2. Well, remember that because I have a versioning system in place, updating, what does it mean to really update the value? What it really means is to add a new version. So maybe there was version 3 of the value that was set to 1. I'm going to create a version 4 that is set to 2. What does it mean? My version 3 with the value of 1 stays there. It's still in there. Maybe it's stored on HDFS. But what I will add into my mem store is a new version, version 4, that has the value 2, right? So this is the trick. You don't delete anything ever. You just keep adding new versions, right? Well, not ever. You still delete them at some point. I'll come back to that. But when you do add it, you just add a new version. So in the strange world of versioning, updating a value really means you create a new version. And deleting a value really means you create a new version that says it's deleted, right? So you never ever modify or delete anything. You just keep adding new versions. That's the trick. Does it answer your question? But how do they keep the order? Oh, so the order of the physical files, remember that when you flush it, it is ordered. And then we don't modify it ever again, right? So within a file, once you've written it, you don't touch it, it's there. So it is ordered. So it means that Within that H file, it's ordered. Within that H file on the left, it's also ordered. Within the mem store, it's also ordered. Within each one of these units, it's ordered. What happens is if you want to look up keys, you just look everywhere, right? So here, there's no particular order. So here you have 3 places to look at, the 2 H files and the mem store. But within each one of them, it's ordered, right? But there is no order across them. So you would need kind of to merge them if you want to have a global order, which we don't. Does it answer your question? Yeah. Just to give you an example, concretely, imagine that these are integers. Imagine that here I could have 1, 4, and 7. Here I could have 2, 3, and 5. And here I could have 6 and 8. Right? So it's ordered within here, it's ordered within here, it's ordered within here. But here, there is no specific order. It's all intertwined, right? That's the idea. Okay. Now, what about this electricity problem? I lose the electricity or there is a crash, the machine crashes. Do we really have to lose all of the fresh key values? The users would not be very happy, right? So there is a trick that we have that's called a write-ahead log. The write-ahead log is the journal, just like when you're in a ship and the captain keeps a journal. So you keep a log of all the incoming updates. So whenever the user adds a new key value, the first thing you do before even putting it in the mem store is you log it in the journal in the order of arrival, right? So it means that we have on HDFS a file called an HLog that keeps track of all the key values you add, but in the order of arrival. They are not sorted by key in the log, they are sorted in order of arrival. And the reason it works is that in HDFS, I cannot modify a file, but I can append at the end of a file. So if I can append at the end of a file, it means that I can keep appending the new key values that arrive, since it's the order of arrival, so the new ones always come at the end. So that I can do in HDFS. I can keep appending to the HLog. Since the HLog is persisted on HDFS, that I will not lose if there is an electricity shortage, right? So once I have appended the key value to the HLog, then I can put it in the mem store. So there is one on HDFS, one per region server, even across multiple stores. And then I add it to the mem store, right? Now, if we run out of electricity or there is a crash, yes, we lose what there is in the mem store, but we still have it in the HLog. So what I do in that case is I just take the HLog, I resort them by key, and then put them back in the mem store. So I didn't lose anything. So again, I insist, in the mem store and in the H files, the key values are sorted by key. In the HLog, the key values are sorted by the order of arrival, the time of arrival. Okay, which is why we can append. All right, and then once we have that, the idea is that we need to figure out when to flush. Flushing, remember, is when we copy over the entire content of the mem store to a new H file. So we can say, for example, when there is a maximum size in the mem store, for example, I can say on the scale of the cluster, if I have more than, I don't know, 1 terabyte worth of key values in my mem store across the entire cluster, then I flush. That can be one design decision. Or I can do it at the size of one machine. If on one machine I have, let's say, more than 1 gigabyte worth of key values in my mem store, then I flush. Or I could also do it based on the write-ahead log. So the write-ahead log is the H log here. I could also say, okay, my log now is too big, so that could also trigger a flush, right? And once I have flushed, I can delete the H log. I don't care anymore, right? Because it's in the H file. Okay, so this is when to decide when to flush. Okay. So now I have an animation on what happens if we want to read. So imagine I'm in the middle of the usage of the cluster. I have already persisted 2 H files to disk, and I have more fresh key values in the mem store. I didn't put the H log, but it's somewhere there at some other place. Now, if I want to read key values because I have a query incoming, and let's say the user is looking for a specific interval of keys, right? A specific interval of row IDs for a specific column family. We need to find them. Where do we look? The user wants to query to look up a specific key or a specific row ID, let's say. Where do we need to look? On Zoom? Well, the answer is everywhere, because we don't know. Could be in the H file, could be in the main store, could be anywhere. So we just need to look everywhere. So we look, maybe there are some in the H file on the left, maybe there are some in the H file on the right, using these indices that I told you about. Maybe there are some in the main store, but since it's in the memory and I told you it's pre-sorted, it's easy to find. And then I gather all of these key values that I found at all of these places, and now I can give back to the user. For whom does that make sense? Who understands that we need to look everywhere? Right? Could be anywhere, we have no idea. It could be fresh, could be old. If you query a key value, you have no idea how old it is, right? So we look everywhere. Now, the problem of looking everywhere is that if you let your system evolve for days, for weeks, for months, what if you end up with, imagine you flush, I don't know, every 2 hours you flush. Then after 1 day, you have 12 H files. After a month, you have 360 H files, and so on, right? So that's a lot of H files. So you just keep accumulating new H files. So imagine that at some point you have 10,000 H files. And now there is an incoming query. You need to look at the name store, and at each one of the 10,000 H files, that cannot be, that's too slow. That is impractical. So we need to find another trick to basically avoid that the number of H files grows too much. Yes? No, we don't need that because the HLog has exactly the same content as the mem store, right? The HLog is the same as the mem store. It's just that it's persisted on HDFS in order of arrival. So this is why we don't need to look at the HLog when we look up. Okay, it's a duplication. Okay, yeah, you're welcome. So imagine we have flushed a lot of H files and we have too many of them. What can we do? We can do what's called a compaction. A compaction means, let's say we want to compact these 3 H files. We can in fact merge them to a new bigger H file, right? Remember that within each one of these, the key values are sorted, but across these, they could be intertwined like this, right? So we can just merge them in a larger sorted list of key values and then write back as a new H files to HDFS. So I had 3 H files. I write a compacted version that is a larger merged H file, and I can delete the other 3, right? This is called compaction. How long do you think that takes, the compaction? So who is familiar with algorithmic complexity? Some of you. Who is not at all familiar with algorithmic complexity? Okay, I'm going to quickly explain. So the algorithmic complexity is the vocabulary that the computer scientists have. And the idea is that when you have an algorithm, which is a recipe for solving a problem, and you increase the size of the problem. For example, the problem could be a puzzle. Imagine that you have a puzzle with 100 pieces. You know how to solve it. Then you have another puzzle with 1,000 pieces. Maybe you have another puzzle with 5,000 pieces. How much more time does it take to actually reassemble the puzzle? Well, one of the ways could be what we call linear. It means that if the puzzle is twice as large, then it takes me twice as much time, right? This is called linear, right? So if I take an hour to assemble a puzzle of 100 pieces, then I'm going to need 10 hours to assemble a puzzle of 1,000 pieces, right? This is called linear. Then there is the complexity that is constant. Imagine that I'm a magician. I just snap my fingers to assemble the puzzle. The puzzle has 100 pieces. I snap my fingers, it's assembled. The puzzle has 1,000 pieces. I snap my fingers, it's assembled. Same amount of time. This is called constant time, also known as O of 1. O of n for linear, O of 1 for constant. Then there is another kind of complexity that's called exponential. We are very scared of that one, computer science. Exponential basically means that every time you add a piece, it, let's say, doubles the whole time. So imagine I have 100 pieces, it takes me 1 hour. 101 pieces takes me 2 hours. 103, no, I'm already lost. 100 pieces takes me 1 hour, and 101 pieces, 2 hours. 102 pieces takes me 4 hours. 103 pieces take me 8 hours. Every time I add a piece, it doubles. This is very scary. We dislike that in computer science. And yet, there are problems that work like that. For example, when you have to decompose an integer into prime factors, this is very hard, and it doesn't scale in that way. It's exponential in the number of bits. So this is what cryptography is in fact based on, because it's as soon as you make the problem size bigger, it doubles every time, so it's impractical. This is called exponential. And there is a fourth, well, there's many of them, but just the basic. There is a fourth one that's called logarithmic. Logarithmic is the opposite of that. It means that every time you double the size of the problem, it adds a constant amount of time. So in terms of my puzzle, it would basically mean that you have a puzzle of 100 pieces that you solve in 1 hour. 200 pieces, you can solve it in 1 hour and 30 minutes. 400 pieces, you can solve it in 2 hours. 800 pieces, you can solve it in 2 hours and 30 minutes. 1,600 pieces, you can solve it in 3 hours, and so on and so on. Every time you double the puzzle, it adds a constant amount of time. This is called logarithmic. So O of 1, O of log n, O of n, O of exponential of n. So this is basically how computer scientists measure the efficiency of an implementation. Now, the thing is, when you want to sort, sorting in the MEM store is a bit worse than linear. It means that sorting, if you have a problem size of n, technically sorting the key values, if you have n key values, takes n log n. Who already knew that, the n log n for sorting? Maybe some of you are already familiar. So basically, it's more than linear. It's a bit more than linear. But the thing is, when we want to merge these H files, you might think, okay, the worst case, that would be n log n because we need to sort. But the H files here are already pre-sorted within H file. So in fact, the time it takes to merge these H files is linear, right? So if I have n key values in all of these files, the time it takes me to compact them to a larger one is in fact proportional to n as well. So this is considered quite good for a computer scientist, right? And in fact, you cannot do better than that, because even just writing the H file would anyway be linear, because you need to write one by one the key values. So you can anyway not do better than that. So this is highly efficient. Okay, so that was a small parenthesis on algorithmic complexity, 101 of algorithmic complexity. Okay. Now, the way that computer scientists think about these things is that they have structures that they call B+ trees and LSM trees. B+ trees, we'll see them in a couple of weeks when we look into indices for MongoDB, for example, so I leave them aside. This is for very popular in the database systems of a small scale, right? When you have the data on a single machine, you store the data in trees like that. But in big data systems, we use a technique called LSM tree. It means log structured merge trees. Sounds very complex, but in fact, I already explained it, kind of the components to you, because I told you what flush is about and what compact is about. And in fact, an LSM tree is just a protocol that says when you flush and when you compact. That's pretty much what it is. So after the break, because now we should take a break because it's 9, I will go into this idea of the LSM trees. And again, to make it simple, this is just about when do we flush and when do we compact in order to keep the performance of HBase optimal. Okay? So thank you very much for your attention. I'll see you in a quarter of an hour right after the break to continue.